Lesson 8.3.2, Statistical Tests for the Difference in Two Population Proportions. Introduction. In the previous lesson, we began testing hypotheses that compare two population proportions. We learned that when the sample size is large enough, the test statistic z is equal to, remember you take the difference in the samples minus the difference in the population proportions divided by the standard error, which is given by that square root right there. Okay? This has an approximately normal distribution and may be used to test claims regarding the equality of population proportions. Our approach was informal. In this lesson, we will discuss the topic of hypothesis testing in greater detail. Try these. Here in the US, we have been hearing about the effects of global warming, but we are interested in whether there has been any change in people's opinions about global warming. In 2 consecutive years, 2010 and 2011, the Pew Research Center conducted polls to find the proportion of adults in the US who were concerned about the effects of global warming. The results of the 2 consecutive polls seemed to indicate that there had been a change in public opinion over this time. Suppose that we decide to test the claim that the proportion of adults in the US who were concerned about the effects of global warming changed from 2010 and 2011. We gather independent samples. In the initial year, 2010, our data tells us that Xi is equal to 233 out of Ni equals 359 randomly sampled adults were concerned about global warming. Don't let those subscripts scare you. The I just stands for initial here, okay? So what we're saying is that in 2010, out of 359 randomly sampled adults, 233 were concerned. The following year, 194 out of the random sample of 352 adults were concerned about global warming. Using a 1% significance level, we can now test the claim that the true population proportions are different. Step 1, determine the hypothesis. When testing for the difference between two population proportions, the null hypothesis states that the population proportions are equal. So last time we wrote that as a sentence, but we didn't write it using symbols. So when you write the null hypothesis, you always put that one P equals the other P. So in this case, P1 equals P2. Or you can also write that P1 minus P2 is equal to 0, right? So this guy right here and this guy are the same thing. Okay, you write down the one that that you feel more comfortable with, okay? What about the alternative hypothesis? The alternative hypothesis, remember, is one of the following 3. It's P1 is less than P2, P1 is greater than P2, or P1 is not equal to P2. If you use a less than symbol, it's going to be a left-tailed test. If you use a greater than symbol, it's going to be a right-tailed test. And if you just use a not equal to sign, it's going to be a two-tailed test. So for the global warming test, we claimed that the proportions of people concerned about global warming were different for the 2 years under consideration. Different here is the key word. We're going to come back to this a little bit later. Okay, so let PI represent the proportion of adults in the US who were concerned about global warming in the initial year. And then let PF represent the proportion of adults in the US who were concerned about global warming in the following year. Remember, I and F, usually you can think of them as initial and final, okay? What is the null hypothesis for this test? Well, we're going to write this down, okay? The initial is equal to the final, okay? Yes, you always put an equal sign for the null hypothesis. That's true in every hypothesis test that we ever do in this class, okay? So if your null hypothesis does not have an equal sign, you're doing something wrong. Okay, now you could have written this, so just so I can show you guys an alternate way of doing this in red, you could have also written Pi minus Pf equals 0. Okay, that's just another way of writing this, but they mean the same thing. Okay? All right, what is the alternative hypothesis? Are we going to use the less than, or the greater than, or the not equal to? So the key here is to read what the scientists think, okay? There are two clues, right? Up here, when we were reading the problem, notice they use the word different. We can now test the claim that the true population proportions are different. Sorry about that. Let me scroll back. So we have the word different there. We also have the word different that I boxed over here in number 1 statement, right? So different just means not equal to, right? If they had said we're concerned that that people care more now than they used to, or the claim is that people care more in the past than they do now, then we would do the inequality going one of the two ways. However, in this case, the alternative hypothesis is Pi is not equal to Pf. Okay. Now, what's the other way of writing this? So the other way of writing this would be Pi minus Pf is just not equal to 0. Okay, they mean the same thing, okay? If one thing doesn't equal the other, then that's the same as saying that when you subtract them, you don't get 0. Okay? So again, use the one you like better. I like the one on the left better, so that's what I'm going to use, okay? All right. Is this a one-tailed or two-tailed test? Think about the alternative hypothesis. How do you know that this is a one- or two-tailed test? Okay, so I'll just say since we have a not equal to symbol, the test is two-tailed. Okay. All right, let's keep going here. So step 2, collect the data. In order to perform a hypothesis test for the difference in two population proportions, we must make sure that the underlying sample distributions for each sample are approximately normal. We will consider the normality criteria satisfied if there are at least 10 successes and 10 failures in each sample. For the global warming test, count the number of successes and failures in each sample. In this test, a success is a person who is concerned about the effects of global warming. So first, for the initial year, how many successes and how many failures were there? Well, it told us in the sample that we collected in the initial year that there were 233 out of 359 adults, right? So 233 out of 359. So 233. Now don't put 359 over there. We're going to just do 359 minus 233, right? Because all the ones that weren't successes have to be failures, right? So what would that be? That would be 126. So that means that if there were 233 successes, then that means there's 126 failures. Okay, what about for the following year? So let's go over to our data. It says that 194 out of 352 adults, 194 out of 352. So 194 successes, and I'm going to do 352 minus 194. What does that give us? This should be 158. Okay, if you use your calculator, that's what you get. So I put 158 right here. Okay, so that's the number of successes and failures. So are these successes and failures enough to consider that the approximate normality criteria have been met? Well, yes, because they are all bigger than 10, aren't they? Also, I just want to check something really quick. Did the problem say that these were randomly selected? Yes, you notice how it says randomly sampled adults for both of them? So you always need to check to make sure that they are random as well. So I'm going to say, since all successes and failures are at least 10, and the samples were random, sorry about that, the normality criteria has been met. Okay. Next, the sample proportions. P1 hat equals x1 over n1, and P2 hat is equal to x2 over n2. Estimate the population proportions P1 and P2 respectively. And so their difference is just going to be P1 hat minus P2 hat. Now, in general, our formulas are going to have 1s and 2s, but remember, in this problem, we have i's and f's, right? So for the global warming test, we're going to calculate pi hat and pf hat. So what is pi hat? Pi hat is equal to, there were, remember, 233 successes over 359, right? 233 out of 359. So we use our calculator and we figure out what we get. So when I do 233 divided by 359, I get 0.649. 0.649. And now I'm going to do PF hat. Right, let's figure out this proportion, okay? So remember, that was 194 out of 352. Let's see what our calculator says. 194 divided by 352. I get 0.551. It looks like they're different, right? But again, what we're trying to figure out here is, are they different enough that we're sure it's not just luck in our sample drawing, okay? Okay, so calculate the observed difference now. So now we just need to subtract them. So we're going to do pi hat minus pf hat. This is going to be 0.649 minus 0.551. So if I do that in my calculator, let's see what we get. I get 0.098. So this is their difference, okay? That's everything for step 2. So we're going to move on now to step 3, assess the evidence. We use a sampling distribution of differences between sample proportions to assess the likelihood of the observed difference occurring. As we have seen, the test statistic for the two proportions test is, remember, this is the formula for the z-score. We're going to do the sample difference minus the actual population difference divided by that square root pooled formula. Okay? The test statistic is a z-score for the difference in the observed sample proportions. To find the z-score, we first subtract the mean of differences P1 minus P2 from the observed difference and divide by the standard error of differences. Okay? The null hypothesis indicates that we should use P1 minus P2 equals 0 for the mean of differences, and the formula also requires the pooled proportion. P bar equals x1 plus x2 divided by n1 plus n2. Remember, you add the total successes, okay? So let me remind you guys that therefore, this is going to end up being the total successes divided by the total sample size. All right, so they actually calculate this for us. Remember, there were 233 and 194 successes. So you add those two numbers up, and then the bottom is 359 plus 352. You add those up, and then you divide them, and you get 0.601. Please make sure that you try this in your calculator and that you understand how to get that. Next, the standard error of differences. So they actually do this for us. I do recommend you plug it into your own calculator, but remember, okay, you have this 0.601 that you get from here. This is what you end up using in your formula, okay? So you put that in this formula, and we have done something like this in our calculator many times before. You end up with 0.037, okay? Remember, this is the standard error. To compute the test statistic for the global warming study, use the difference in the observed sample proportions and the estimated standard error. So this is what we're going to calculate. We're going to calculate the z-score. And why does this go away? Remember, this you get from the sample, but this you get from the null hypothesis. Remember, you're assuming that the null is true, and if we come back to our null, if they're equal to each other, that's the same as their difference being 0, right? So if their difference is 0, that's why you're basically just allowed to ignore that second part, okay? This essentially is going to go away. So that's why if you look at what they wrote next, it actually just disappears and you end up just using that, okay? Okay, so let's go ahead and figure out what the z-score is. Remember, we had a difference. We calculated that difference in 3b, so let's come back here. 3b was 0.098 for my difference. So it's going to be the z-score is equal to 0.098. Remember, we're subtracting 0, so it's like there's nothing there. And we're going to divide that by the standard error, which is 0.037. So what do we get when we subtract these? Sorry, not subtract, divide them. We do 0.098 and we divide it by 0.037. We end up with 2.65. 2.65. Okay, part B. How many standard errors is the observed difference from the assumed mean of differences of 0? So our observed difference is 2.65 standard errors above the assumed mean of 0. Okay, that's exactly what a z-score is. Remember, that's the number of standard deviations. So let's look at part C. Does this observed difference seem to be unusually far from the assumed mean of differences? Why or why not? Yes, it is unusually far since it is more than 2 standard errors away from the mean. Okay, so this is probably going to end up being significant, but again, let's not jump to conclusions here. We're going to get to the answer in a moment, okay? So let's revisit the concept of the p-value in a hypothesis test. The p-value is the probability of observing a z-score that is at least as extreme as the test statistic, assuming the null hypothesis is true. Recall that there are 3 types of hypothesis tests. For a left-tailed test, where the alternative hypothesis is P1 is less than P2, you're going to shade to the left of the statistic, right? So that's the p-value. And we're talking about the p-value, right? For a right-tailed test, when the alternative hypothesis is P1 is greater than P2, then the p-value is the area to the right of the statistic. So this would be the p-value. For a two-tailed test, where the alternative hypothesis is P1 is not equal to P2, the p-value is twice the area to the right or twice the area to the left. But either way, remember this is called a two-tailed test. So for this, remember the p-value is that piece plus that piece, but they are the same because of symmetry, and so we could just calculate either side and then double it. Okay, sketch the standard normal curve and identify the position of the test statistic and shade in the area that corresponds to the p-value. So it looks something like this. And if we go 1, 2, 3 standard deviations, 1, 2, 3 standard deviations, right? So this is 0, 1, 2, 3, -1, -2, -3. Then the place where we shade is, remember we got Didn't we get 2.65? Is that right? Yes, 2.65. So this means I have something like that. But then I also have the other side, right? So that would be the p-value, okay? So this is, let me go ahead and also mark down that this value right here is 2.65. And then this value right here is negative 2.65, right? Okay, so this is what we are shading here. So write the p-value below. Remember that the tails area is doubled for the p-value of a two-tailed test. So we are going to use Normalcdf, right? That is how we find the area under a curve. Well, that's normal. So it's going to be normal. Sorry about that. It's going to be normal CDF. The lower limit is, so what I'm going to do is I'm going to do the right side. It's 2.65 and then 1E99. Now remember, I need to do 2 times all of that. 2 times all of that. We're doubling it because it's a two-tailed test. Okay. So I'm going to cut to the calculator now. So let's remember how to do this in our calculator. Coming over to the calculator, I'm going to actually start by doing 2 times. So 2 times, that way I don't forget to double my answer. Second, DISTR, go down to Normalcdf, hit enter. And I have 2.65, 1E99, and then I will hit paste, enter again. We get 0.008. So on the calculator, we got 0.008. Okay, so let's keep going here. Important things to remember about the p-value. When we assume that the null hypothesis is true, we're assuming that 2 population proportions are equal. Then we can think of the p-value as the chance that the observed difference in a sample proportions is due to chance variation. When the p-value is small enough, we no longer believe that the difference between population proportions is likely to be 0. In this case, we reject the null hypothesis that the population proportions are equal. We say that our sample data supports the alternative hypothesis. When the p-value is too large, we do not reject the null hypothesis. We say that our sample data do not support the alternative hypothesis. We decide whether a p-value is too large or small enough to reject the null hypothesis by comparing it to our chosen significance level, alpha. Interpret the p-value in the context of this problem. So this means if we assume, what was the, let me remember here, we're talking about the proportion of people in the US that were concerned about the effects of global warming from 2010 and 2011. So if we assume the proportion of people who are concerned about global warming is the same in 2010 and 2011, the probability of obtaining a sample difference at least as extreme as the one we observed is 0.008. Okay. Sorry, that does not look good. Let me erase that. Let me draw a better 8. There we go. Okay. Step 4, state a conclusion. It is important to explain the result of your test in a way that is easy to understand. Remember that the hypothesis testing process is not perfect. So when you explain the result of your test, make clear that there is some uncertainty. A conclusion can express support for the alternative hypothesis. The strongest support we ever give to the null hypothesis is to say that we cannot disprove it. It is always wise to indicate that the conclusion was based upon sample data. For the global warming test, make a decision using the p-value and alpha. What is the significance level? So I don't remember what the significance level was. Was it 1%? I think it was 1%, but let me just make sure. Yes, using a 1% significance level. Okay, so they want us to be really sure, right? Because 1% is a very strict condition. So alpha is equal to 0.01, right? That's 1%. Okay. Use the p-value to make a decision regarding the null hypothesis. Well, we got 0.008, and that is indeed smaller than 0.01. What does that mean? This means that's small enough, so we reject the null hypothesis. Okay. Let's go to part C here. Think about the global warming surveys. State a conclusion in the context of the surveys. All right, so since we rejected the null hypothesis, we are going to support the alternative, right? So what is the alternative? The alternative is just that the proportion of people who believe in global warming has changed. That's all, right? You can see it right here. PI is not equal to PF. Okay. So let's write it like this. At a 1% significance level, the evidence supports the claim that the proportion of people in the US who are concerned about global warming changed from 2010 to 2011. Okay. again, if that p-value had been larger, then we wouldn't say that it stayed the same. Instead, we would say that it does not support this claim. Okay, but we can never confirm the null, right? We're not proving the null is true. We're just trying to see if there's evidence that supports the alternative or not. Okay. Let's look at another problem, okay? Sharon P. Fowler and her colleagues at the University of Texas Health Science Center, San Antonio, conducted research about people who drink diet sodas. The researchers' findings suggest that people who drink diet sodas can actually show weight gain rather than weight loss. The following simulated data are based on this diet soda study. Suppose that in a random sample of 910 people who drink half a can of diet soda per day, 239 people are obese. That is, very overweight. In a random sample of 832 people who drink 1 can of regular non-diet soda per day, 252 are obese. We will test the claim that the proportion of people who are obese is lower among people who drink half a can of diet soda per day than among people who drink 1 can of regular soda per day. We will test this claim at the 5% significance level. Okay. So, step 1, determine the hypothesis. Define PD to be the obesity proportion among people who drink half a can of diet soda per day. So D is for diet, right? Define PR to be the obesity proportion among people who drink 1 can of regular soda per day. What is the null hypothesis for this hypothesis test? Remember, the null hypothesis is always that the two are equal to each other. What is the alternative hypothesis? Well, that we need to read amongst the problem. It says we will test the claim that the proportion of people that are obese is lower among people who drink half a can of diet soda per day than among people who drink 1 can of regular soda per day. So it's lower. So it's going to go like this, is less than PR. Okay? Now, let's make sure that they didn't want it in a different order. Yes, it's okay. We're good. Now, by the way, remember I said there was an alternate way of writing these? So you could also write that PD minus PR is equal to 0. And then over here, PD minus PR. Now be careful, that sign does not change, so less than 0. Okay? Remember, if something is smaller, then that means if you subtract something bigger from it, you get a negative number, right? Okay. Is this a right, left, or two-tailed test? And how do you know? Well, there is a less than symbol, so since the alternative uses a less than symbol, it is a left-tailed test. Okay? All right, let's keep going here. Step 2, collect the data. Verify that the criteria for approximate normality are met. Approximate normality. Okay, so remember we had 910. So let me write it this way. First for diet, and then for let me write it as regular. Now, it's funny, guys, but in this problem, we are considering a success as being obese, right? Because that's the criteria that we care about. Okay, so let's look first at diet soda. It says that in a random sample of 910 people who drink the diet soda, 239 are obese. So that means 239 out of 910. 239 successes. And what's 910 minus 239? Because that's going to tell us how many people are not obese, right? So if you do 910 minus 239, you get 671. So 671 failures. So for people that drink regular soda, it says 252 out of 832. 252 out of 832. So what's 832 minus 252? 832 minus 252 is 580 failures. And were the samples random? Let's make sure. Let's see here. It says a random sample, right? There's the word random sample. There's the word random sample. So yes, we need to write that too. Sample was random. Or samples, right? We had two of them. Samples were random. So this means, and these all are at least 10. So normality criteria is met. Okay, let's go to the next part. It says calculate the sample proportion of people who drink half a can of diet soda per day who are obese, PD hat, and then we also want to calculate the sample proportion of people that drink a regular soda per day who are obese. So for the diet soda, remember we had 239 obese people out of a sample of 910. So our PD hat is equal to 239 out of 910. So if we divide those, we get 0.263. And if we do PR hat, remember we had 252 obese people out of 832. So if we divide that number, 252 divided by 832, I get 0.303. Next, compute the difference in the observed sample proportions, PD hat minus PR hat. Well, PD hat minus PR hat is equal to 0.263 minus 0.303. So if you subtract these in your calculator, be careful you're doing a smaller minus a bigger number. So as expected, we get a negative answer. It's negative 0.04. We expected a negative answer. Again, remember, that's the claim, right? The alternative is that it is negative, right? Okay. Next, let's find all of these. So first, we're going to find the pooled proportion P bar, right? So P bar is going to equal, we add up all the successes. So it's 239 plus 252. And we divide that by, we add up all the sample sizes, which in this case is 910 plus 832. 910 plus 832. So 239 plus 252, when I do the top two and add them together, I get 491. And the bottom, 910 plus 832, you get 1742. Okay, so that's what I got. And when I divide that, 491 divided by 1742, I end up with 0.282. That's the p-bar, so that's what I'm going to use in the next formula for the standard error. Okay, so let's go ahead and put that in the square root. Remember, it's 0.282 times 1 minus 0.282 divided by the number of people in the diet sample was 910 plus, then we have 0.282 times 1 minus 0.282, and that's divided by 832. Okay. So I'm going to use my calculator, and let's see what we get. Okay, so let's see what the calculator gives us. So we're going to hit second square root, and then I have 0.282 times 1 minus 0.282, close parentheses, divided by 910, and then plus 0.282 times 1 minus 0.282, close parentheses, and then divided by 832. So when I hit enter on this, I get 0.022. Okay, 0.022. Okay, so our calculator told us that we get 0.022. Remember, that is the standard error, and so when you find your z-score, that's going to be what goes in the denominator, right? Now, remember, this part is obtained from the sample, and this part is obtained from the null hypothesis. Now, if you recall, we look at the null hypothesis. The null is always that part is 0, right? So that part goes away, and so that's why in the next part, we just have the sample difference divided by the standard error, okay? So I'm going to divide those two. Remember, the sample difference is negative 0.04, and I'm going to divide that by the standard error, which is 0.022. So let me go ahead and figure out what that is. Just dividing those two numbers in the calculator, I end up with negative 1.82. Negative 1.82. How many standard errors is the difference from the assumed mean of differences? This is just making sure that we understand that what a z-score is, right? A z-score always tells you how many standard errors away something is from the mean. So I'll say PD hat minus PR hat is 1.82 standard errors below the mean. Why is it below the mean? Well, remember, when a z-score is negative, that tells you that we are that many standard deviations below the mean. If it were positive 1.82, then that would mean that it's 1.82 standard deviations above the mean. Okay, so let's keep going here. Part C. Does the test statistics seem to support the claim that the obesity proportion is lower for people who drink half a can of diet soda per day? So the answer is yes. Since z equals negative 1.82 is less than 0, this means that PD hat minus PR hat is less than 0, right? Again, if that happens, right, then that means that PD hat, so i.e. PD hat is less than PR hat. right? If that happens, then that means that the diet soda drinkers have a lower obesity proportion than the regular soda drinkers, right? And that's exactly what they are asking. Okay, let's keep going. Use the test statistic to determine the p-value. Sketch the normal distribution, identify the position of the test statistic, and shade the area that corresponds to the p-value. Okay, I'd like to do the sketch first so that we can get an idea of what we're talking about. So if this is our sketch, 1, 2, 3 standard deviations, and then 1, 2, 3 standard deviations. Let me go ahead. So if those are each standard deviations, remember we are at negative 1.82, right, for a z-score. So what that means is that we're about right here. So we are at negative 1.82. So that is the p-value. The p-value is the shaded part in here, right? That's what we are interested in. We want to know if that tiny little area is small enough for us to consider this statistically significant. Okay, so I'm going to do the p-value now. The p-value, remember, that's given by Normalcdf in the calculator. And we're going to do negative 1e99, and then we have negative 1.82 is the upper limit, okay? So that is going to be what we put into our calculator for Normalcdf. So let me jump over to the calculator so you guys could see it. Okay, guys, let's go ahead and check out our Normalcdf function on our calculator. So I'm going to hit second distr, go down to Normalcdf, hit enter. This time our lower is the negative infinity, so I'm going to do negative, remember the negative symbol is down here, 1 second EE, and then 99. The upper limit is negative again, 1.82. Go down to paste, hit enter, and if we round it to 3 decimal places, we get 0.034. And we get 0.034. Or you can also round that to 0.03. When you're doing a p-value, all that really matters is the first digit, okay? But sometimes if it's like really close to the alpha, the significance level, we do want more digits. But for now, this will be fine. Okay, so this is our p-value. So it says, interpret the p-value in the context of this problem. Okay, so what does the p-value mean? So if we look at our p-value here, we end up with, or if we look at our p-value here, we wanted to look at the actual context of the problem. And remember, we're talking about percentage of obese people among diet soda drinkers versus regular soda drinkers. So we always start the p-value, the probability statement looks like this. If we assume the null hypothesis, right, which is if we assume the proportion of obese people is the same among diet and regular soda drinkers, the probability of observing a sample difference at least as extreme as ours is 0.034. Okay? All right, so that is what the p-value means. And so let's go to our significance level. Now, I'm not sure of the significance level because I need to go back and look. Again, it's always stated by the problem itself. And it does say here, we will test this claim at the 5% significance level. Okay, so coming back here, alpha is equal to 0.05, right? Because it says 5% significance. Do you reject or do you fail to reject the null hypothesis? Well, since the p-value is smaller than alpha, isn't it? So because 0.03 is smaller than 0.05. So that means we reject the null hypothesis. Okay? All right, let's keep going. This hypothesis test focused on the relationship between obesity and whether or not people drink diet soda or regular soda. Write a conclusion to this hypothesis test. In your conclusion, explain what you believe the data suggests about this relationship. Okay, so we need to understand here that what we showed is that the evidence, the sample that we took supports the alternative hypothesis. So what is the alternative hypothesis? Remember, the alternative hypothesis is that PD is less than PR. What does PD less than PR mean? It means that the proportion of obese people amongst diet soda drinkers is less than the proportion of obese people among regular soda drinkers. So let's go ahead and write that down. So start with the significance level at a 5% significance level. The evidence supports the claim that the proportion of obese, let me write it this way. The proportion of diet soda drinkers that are obese is less than the proportion of regular soda drinkers that are obese. Okay, so this is how I would write the conclusion to the hypothesis test. All right, so before we move on to the next part, your code word for this lesson is Pepsi. Okay, like the soda, Pepsi. Okay? So let's move on. Let's look at number 13. Use technology to compute a 90% confidence interval for the for the difference in population proportions, PD minus PR. Now, we have not done a confidence interval in a few sections, right? Because we've been learning about hypothesis testing. So we're doing this so that we can approach this data in two different ways, right? Before, what we just answered was a hypothesis test, but now we're going to approach the same thing using the confidence interval approach. So using our samples, let's go ahead and construct a confidence interval. So we're going to plug in what we know for this margin of error formula. Everything's written there, so we're going to write it all down. We have 1.645 times the square root of PD hat. Now, let's go back. What was PD hat? I haven't seen that in a while, so let's see. PD hat was all the way over. PD hat was 0.263. PR hat is 0.303. 0.263, 0.303. So 0.263 and then 0.303, right? And what were the sample size? Let's come back here because I don't remember that either. Sample sizes. I believe that one is written right at the beginning, right? Let's see. So 910 was the sample size for the diet, 832 for the regular. So 910 and 832. So this is what we're going to put in our calculator, okay? This is a complicated calculator function, but I want to show you guys how to do that all at once in the calculator. So let's see what our calculator says here. So it's going to be, I'm going to write down the 1.645 first, times, and then I'm going to put second square root, and then I'm going to put 0.263 times 1 minus 0.263, close parentheses, divided by 910, and then plus 0.303, open parentheses, 1 minus 0.303, close parentheses, divided by 832. So all of that gives me 0.036 after rounding. Okay, so it's 0.036. This is the margin of error, okay, for 90% confidence. What is the confidence interval going to be? Remember, we have to do PD hat minus PR hat minus the margin of error, and PD hat minus PR hat plus the margin of error. Okay, so what were they when we subtracted it? Remember, we got negative 0.04. Let me just make sure that's correct up here. So when we subtracted them, yes, we got negative 0.04 for 10C. Negative 0.04. So here we get negative 0.04 minus E. Okay, so if you put that in your calculator, don't forget that the first guy is a negative sign, but the second one is a minus sign. If you put that in your calculator, you should get negative 0.076, okay? And then if you do negative 0.04 plus 0.036, I get negative 0.004. So the confidence interval is negative 0.076, negative 0.004. Okay, this is the 90% confidence interval. Okay. Answer the following questions based on this confidence interval. Oh, before we move on, remember guys, this is where PD minus PR lives, okay? It lives inside of those two numbers. Remember, this is a difference that we're talking about, okay? So let's keep going here. Answer the following questions based on this confidence interval. Part A, can we conclude which population has a higher obesity rate? That is, can we conclude that the people who drink half a can of diet soda have a higher obesity rate, or can we conclude that people who drink 1 can of regular soda have a higher obesity rate? Explain your answer. Okay, so I want you guys to pay attention to this confidence interval. Does it ever cross 0? The answer is no, because it's negative the entire time, right? So based on the 90% confidence interval, since it is negative the whole time, this means that PD minus PR is less than 0. Okay, is less than 0. Remember, for that to be true, this is the same as PD being less than PR. Okay? So this implies that diet, or they're asking us who has a higher obesity rate. So let me just say regular soda drinkers have a higher obesity rate. Finally, last part here. How does our conclusion relate to the hypothesis test? Explain your answer by thinking about the values in the interval. So, what does this mean? So here's the thing. We have two ways of analyzing things, right? With a hypothesis test and with a confidence interval. Earlier in Module 8, we talked about confidence intervals and we practiced doing that. And that is when we are presenting where we think the real answer sits. And then later we talked about hypothesis testing. So let's look at our hypothesis testing. This was our result, right? We said at a 5% significance level, the evidence supports the claim that the proportion of diet soda drinkers that are obese is less than the proportion of regular soda drinkers that are obese. In other words, the obesity rate is higher for regular soda drinkers. And then what did we conclude over here? Again, we actually concluded the same thing, didn't we? That regular soda drinkers have a higher obesity rate. Why? Again, because it is negative the entire time. If it went from negative to positive in the confidence interval, then we can say that we're not sure which one is bigger, right? Because 0 allows for the possibility that they are equal to each other. So, the confidence interval agrees with the hypothesis test result. Right? PD minus PR is negative since all values in the confidence interval are negative. So this means that PD is less than PR. Okay, this is a good problem because we got to practice confidence intervals, but we also got to practice, of course, the hypothesis test concept. And that concludes this lesson. Thank you so much for watching this video, and I hope it was helpful.